This is the second detailed tutorial on the new Open Specy 1.0. We're going to go over batch processing and how to analyze your spectra as fast as possible and as accurately as possible. So to get started, I've already gone to the Open Specy, openspecy.org website. You can see more. I'm going to share some links in the chat about some of the other tutorials, so you can see information about all the buttons on this screen and what they mean and what they do, how they work together. You can see information on batch processing really briefly. This tutorial is going to take a really deep dive into batch processing and not focus too much on some of the details of the interface. So for this, we're going to use the test map dataset. Click download here. And the test map dataset is a zip folder. I'll show this to you. The zip folder has two files in it. One is an HDR file, and the other is a DAT file. These two files form what is known as an NV file. So if you have an FTIR mapping device, you can usually export this NV file format and then zip it up into one zip folder, and that will allow you to upload it into Open Specy. Also, for batch download, if you watch the quick tutorial, I showed an example, or for batch upload and batch analysis, I showed an example of how to upload multiple spectral files that don't necessarily have a spatial reference. So if you have like a collection of spectra, you can put them all into a zip folder and do a similar type of analysis. I'm not going to go over that type of analysis too much in this tutorial because that was already covered in the quick tutorial, and this one is really going to take a deeper dive, and a lot of the ideas cross over too. So this is what the test map looks like. And we're going to upload that. So right away, what you end up getting is you get two plots. The first plot is your spectral map. So this is your spatial reference. In this spectral map, we have somewhere around I think it's like a 12 by 12 spatial area where every pixel is 25 microns. And every pixel has a spectrum. So I can look at the spectrum here. I can look at the spectrum here. Look at the spectrum over here. And you may wonder why some of these pixels don't have colors. And that is because the signal to noise threshold isn't being met by them. So those pixels are not yet high enough quality to really consider ready to analyze. We could turn that off for now just so that we can view all of the spectra in this space and see where they're at. So from here, there's really kind of two paths that we could go down when we're considering how do I analyze all 100 of these spectra simultaneously. The first one is that we could do a typical routine as we did in some of the other tutorials. So maybe I'll show that one first. So we can do pre-processing to get the signal to noise ratio high, and then we can do identification and then download the results of that. So we'll go do pre-processing. Signal to noise ratio is pretty high. I'll turn on thresholding here. Right. So in this spectrum, you can see here, I talked about this in some of the other tutorials too. There is a CO2 peak that's being a pain. It is causing my background. So these are background spectra. There's like a gold slide behind a particle. It's causing them to look like they have really high signal to noise, but actually they don't. And so what we can do is we can use flatten region to diminish their effects. So now we got that area flattened out, and now you can see a lot more of those pixels in the background are not showing up as having high signal to noise anymore. So we can look around here, look at our signal to noise threshold. It looks like somewhere around 4 is, yeah. So we're currently at 4, and a lot of these pixels are not, a lot of the pixels where I would expect the spectra to be above the signal to noise ratio are not above the signal to noise ratio. So there's really a couple of things that we could do. First, we could just ignore them and say, yeah, the vast majority of the spectra that I have here are the particle that I'm looking for. So maybe that's okay. And I can just move forward and do analysis. So I'll show you that first. We're going to use the AI both derivative meteoid analysis routine because that's extremely fast. And now thresholding by the correlation and by the signal to noise actually ends up doing a lot better job of removing those background spectra. So all we have left pretty much that are the spectra from the particle itself. So if we look over here, that's just noise spectra. And then over here, we have particle spectra. We still have that problem though, unfortunately, of these spectra here actually having, they're still being removed. And so one thing we could consider doing actually is we could consider using the correlation coefficient as a threshold instead of the signal to noise ratio here. Because that's what I'm seeing. I'm seeing that this particle inside of here is really, yeah, there we go. So now we have, let's see, let's take a look at this. Yeah, I can still see some signal there. I can still see some signal there. So, and then here, yeah, less signal. Oops. There we go. All right. So we want to inspect our map. We want to inspect our spectral map to try to make sure that it is fitting what we're expecting. That's a really important part of this. And a lot of times to do this, to make sure that you are getting what you're expecting, is that, you know, for me, I took a photograph of this one particle. So I know that there's one particle and where it should be in the image. So what you should do is reference that visible image and that other image, or this spectral image, and compare the two. And so from this, if this was what we wanted right here, we just wanted to know what are the particle spectra and what are they probably identified as. We can download the top match here, and it will give us the top matches for all of those spectra. And let me show you here what you can do with that. So what we could do, so I said that the main thing that I did was I thresholded by the correlation, and I removed the signal threshold. So what you can do too here is you can use this. You could run a filter, for example, run a filter on this in Excel and filter by all of the true for good correlations. And you would end up extracting out just the identities of those pixels that are the particle. And then you can use that to analyze and say, oh, or what percentage of them are the right type of material that I'm expecting. Some other things to note. So just like with the single spectrum analysis, the batch spectrum analysis, you can pull out a top matches for every single pixel. So here I'm showing that, you know, all of these are saying that it's a cellulose acetate particle. And in fact, this is a cellulose acetate particle. I know because I spiked that on there. And you can look at, the next, if you want to see the next match here and compare that visually. You can compare the following match visually, just to make sure that, if you see any pixels that kind of don't make sense to you, you can interrogate them and figure out, okay, what's going on here? Why is this one not making sense? Another thing too to note is that the XY coordinates of your pixels are on here on the pop out when you hover over the spectral map. And the row number is also an important one. That's going to tell you the number, the spectral number in the data set. Now, another thing that we could do that's pretty useful is we could do what is called thresholded particles. So what thresholded particles does is it is going to take your thresholded image here, and it is going to find particles in the image based on the things that are occurring colored, not the things that are in black. And for this, what it will do is it will find that there's one particle here. It is going to measure the area of that particle in pixels. It's also going to measure the length, the width, and the perimeter of the particle and return all of that information back to you in a special format. So I'm going to download this. And because how we have this set up, we just have one particle, one kind of area that's being outlined in the spectral map. This thresholded particles data set that we're downloading should just have one spectrum when we re-upload it in here. Okay, so I have uploaded the thresholded particles data set, and what you can see is that there's now just one spectrum. This is the median spectrum from all of those pixels that we had outlined where our particle was. This is the median of those spectra, and we can use that to identify what that particle is. This is kind of an alternative routine. Instead of inspecting all 100 spectra, we just try to threshold the particles, take their median, and then analyze the median spectra so we get one spectrum for each particle. This spectra has already been pre-processed, so we don't want to do pre-processing again because it's already the absolute derivative transformation. But we do want to do identification to try to figure out what it is. And this says that it's a 98% match to cellulose acetate. We can also look at some of the top matches, and they're all the same. So that is one kind of workflow that you could go through to try to get after this. Now, I will tell you right away that this is not always going to be the fastest way to do it. I'll show you another example here with the test map, where we actually could have sped up the analysis, especially for really large maps. We could have sped up the analysis by quite a bit. Okay, so I'm going to upload the test map again. Here's the test map. What we can do with the test map is we can run some of these special signal noise thresholding techniques on the data before we even do processing. So with signal over noise, that particle is not really popping out. We actually have some issues here where there's little grid lines in between our spectra, and we don't really see a clear single particle in this image. Well, what if we do signal times noise? Here, I'm going to turn this off actually, so that we can see that better. So signal times noise, now the spectra starts to pop out a little bit, or the particle starts to pop out a little bit. We can see this central particle here emerging. We could also test out signal or total signal. And that actually looks even better to me. These are two different techniques. The signal times noise is going to multiply the mean intensity of every spectra. by the standard deviation of all the intensities. And then the total signal is going to sum up all the signals or all the intensities. And with this, so I'm trying to find where the threshold is. I know that there should be a particle here in the middle. That's what I know. So I know that because I already looked at a photograph of where the particle was taken, was imaged. And so all I need to do is reference this against that photograph and figure out where to assign my threshold. And you could do this, like I'm doing this with one particle right now, but you could do this with hundreds of particles or thousands of particles even simultaneously. So what I'm seeing is that somewhere around 300 or 400, I'm seeing this big drop off in the signal, in the total signal value. So let's compare a couple. You know, this is 250. That's pretty bad signal. That's probably our background. That's not our particle. Now we look at 11,000 signal. That's looking like a particle spectrum. 260 again. Yeah, it's not as good of a spectrum, but it's not horrible. 270, yeah. Let's try one kind of on the edge. 500 looking good. 380 still looking really good. 400. Okay. I'm thinking somewhere around 350 is a good threshold for this. And another thing we could have done instead of going through, or in addition to going through these and trying to look at the spectral quality, is looking at the histogram, because a lot of times the histogram will be bimodal when you have two different groups of identities. And so here we can see that there is a bimodal, there's a mode here in the histogram of all the total signals, and then another one here. And so somewhere around 400, like I was saying, or maybe 350 is a pretty good, probably a pretty good spot. So I'm gonna say 350. And then we're gonna threshold that and see what we get. That's a pretty similar map to what we saw before, a pretty similar threshold. But the big thing that's different here is that what we've just done is really computationally cheap. All we've done is basically summarize the spectra and use the summarized spectra to define a threshold. We haven't correlated it against the library. We haven't pre-processed it or anything like that. And so just from this already, we can actually download thresholded particles again. And now that I've uploaded the thresholded particles, you can see the new spectrum hasn't undergone any processing. All it is the median of all of those pixels that we defined as where a particle is. And again, we just got one spectrum in return. And moving forward, this would be a lot faster for us to just analyze this one spectrum than it would be to analyze all 100. So this is really the beauty of this technique. So we can go forward, and we will want to pre-process this time because that spectrum hadn't undergone any pre-processing. We were just using the signal and noise to try to figure out where the particles were. And then we can do identification again, and we get the same answer. It's a cellulose acetate particle. I also want to say that the data formats that's being uploaded here, that's being downloaded here for thresholded particles, it's called an RDS file. And this is really compatible with the Open Specy R package, which if you're getting into batch analysis and map analysis, honestly, I highly recommend you checking out the Open Specy R package, because it's going to make this workflow extremely seamless for you. You can batch your batches, you know, Just so many great things that we've baked in, and really it's the powerhouse that's making all of this possible in the Open Specy interface too. So these RDS files, I definitely recommend you checking them out. They are called an Open Specy format. They have all this rich metadata in them too about the particle shape, the particle size, perimeters. They have all the spectra from the particles, all that kind of stuff. So, okay, one more thing that I want to discuss is this toggle up here about the good signal. So in general, our goal as spectroscopists is to maximize the signal to noise ratio with our processing routines. And we want to maximize this good signal percentage in as far as it makes sense. So with a mapped spectra, it doesn't really necessarily always make sense that we want all of our pixels to have good signal, because a lot of those pixels may be from the background or something like that, and you actually want them to have the signal that they have, which is bad. It helps you to differentiate them, as I showed before with the thresholding of the particles. But if the data set that I uploaded was a batch data set that doesn't have a spatial reference, it's just a collection of spectra, then we may actually want to try to get that good signal. And we think that, let's say that we think all those spectra are high quality, they should be at least. We may want to get that good signal to go as close to 100% as possible before we do identification. And then even playing around with the identification settings so that we can do that. So I'll just use this map as an example for that. But remember, maps and batch individual spectra are not the same thing. And if you want an example of what batch spectra upload looks like, then for individual spectra, then watch the quick tutorial, because I gave an example of that there. So let's say that we needed to get as many of these spectra above the signal to noise ratio as possible, because anything that's below the signal to noise ratio threshold, we are going to call unknown, basically. So we're going to do flatten region, because like we had talked about before, there was that peak, the CO2 peak. We can look at some of the spectra to see, oh, why does that one seem like it's not high enough signal to noise? I may actually try something here with this to increase the polynomial, see if that has an effect. That's going to make the fit more wiggly. That didn't seem to have too much of an effect. We could try decreasing it. So we went from 62% to 63% when we go up. So actually, it seems like we're getting better as we go higher windows. That's interesting. Okay. Let's see if those spectra still look pretty good. Yeah. Still look decent. All right. We can take a look at our thresholding value here. So we have it set at 4. That's really like probably the lowest. If you're going to use the signal to noise ratio, then that's probably the lowest you want to do. We could bring the polynomial order down 1. Ooh, that's not the direction to go in. So it looks like increasing the window size may continue to help us out a little bit. Okay, so we're at 82% of the spectra are above our signal threshold. That's pretty good. I mean, if you had 20% of your spectra you had to retake or something like that, you know, that's not horrible. And so now we go into identification, and we think about this minimum value for the threshold correlation. We're setting it at 0.7 because that's really, I think, the lowest that you'll want to go. And so now you can take a look, cellulose acetate, so that's still good. You'll want to take a look at these spectra and their matches. Really, the best way to do things is to take a look at the spectra, see if the matches make sense, see if they look reasonable, like reasonable fits. And using these can be a good assistant to you so that you can optimize your tuning parameters. So let's say, okay, we had good signal was 82%, good correlations 83%. That's pretty cool, actually, that we had high correlations for more spectra than the signal. But then our good identifications is only 71%, which is the combination of the good signal and the good correlation thresholds. So at this stage, we might ask, well, should we use a different library? There is the larger library that we could use. So this derivative meteoid is a compressed version of the full library, which is the both derivative. So let's try that. And you'll see right away that the both derivative library is going to take longer. You're comparing against tens of thousands of spectra instead of 300. While that's loading, I can talk about some of these other ones too. So we could also have chosen the FTIR derivative, which is going to look at just FTIR derivative spectra. Right now, we're running against Raman too, which in most cases I've seen it doesn't really matter because the Raman spectra is not going to get misidentified as FTIR in most cases. We could have also used this FTR derivative multinomial, which maybe I will show you after this one finishes up to give you an example of that. Okay, so we got our good identifications up a little bit more, which is a good thing. We want more good identifications. So it took us a little bit longer to do that analysis, but I mean, it wasn't all that long. It wasn't too bad. And now we have more good identifications. And we can go ahead here if we were happy with this and we had inspected the spectra and it seems like, these were the ones that we were going to be able to know what their identity was, then we would download our top matches there. I said I would go over the AI-based identification. So I'll go over that real quick. So this AI FTR derivative multinomial is extremely fast. It actually happened that fast. Doesn't even really show like a loading panel because what it's doing is it is identifying your spectra based on a model, a multinomial logistic regression, and it takes your spectra and it compares it to the model weights, and it says it's most likely to be this or it's most likely to be that. So what's really cool with this model is it's pretty accurate in the domain. This is still kind of experimental, I'm going to be honest. It seems to be really accurate in the domain that we developed it in. So we developed it in taking reflectance measurements of particles on the surface using spectral mapping for FTIR. And it seems like, all these in here that are being identified as cellulose derivatives, that's right. That's what we would expect. You can look at your spectral matches, but there's no way to compare this against a reference library because it's just model weights that are predicting your spectra. You can still download the top matches and it will give you the model identification of everything and how strong that model identification was. So that is available to you. All right. Thank you for your time. And I look forward to seeing how you batch process your spectra in Open Specy.